Okay, off and running to our final chapter, Understanding Research Results. I'm going to zip through this pretty quickly here for you. This is a really relatively easy chapter to finish with, and I don't think you'll have too much trouble here. We're going to talk about ways of describing results. Some of the things that you'll see in this chapter are things that you probably have learned in high school or even before that. But we will talk a little bit about some things that you might have seen in stats, but again, this is not a stats class, so I'm not going to ask you to know any of that. And then we'll talk briefly about correlation coefficients, which again, you've talked about hopefully in your stats classes or in your introductory psychology class, and then we'll end up with something that's a little bit more important, which is effect sizes. But just really quickly, statistics do help us to understand the data that we collect in our research, and that is an important thing to know. And we focus on, with statistics, to describe data that we have collected, but also to make inferences so that we can make decisions. And there are three basic ways of describing results. One is to compare group percentages, another is to correlate scores of individuals on two different variables, and then the final way is the most popular way, which is to compare group means. But let's start with comparing group percentages. So suppose you want to know whether or not males and females differ in their support of Hillary Clinton as president, and obviously this is a little bit dated, so we could put in Obama now, but even then, that's a little dated. And let's say that 60% of female support Hillary Clinton and only 20% of males support Hillary Clinton. So there appears to be a pretty good relationship between gender and the liking of Clinton. And so one thing that we want to note here is that we use percentages because the variable here, gender, is a nominal variable. It's a categorical variable. When you don't have distinct groups where individuals are measured on two variables, you can correlate, or when individuals are measured on two variables, you can correlate individual scores, which is really a nice thing to be able to do. So you can answer questions such as the one that you see here, such as, is there a relationship between location in a classroom, where you sit, and grades in the class? And a lot of research has been done, by the way, on this, and what they have found, interestingly enough, is that there is, and typically people who sit up front tend to have higher grades. And then finally, there's comparing group means, and a lot of research is used to compare mean responses of participants in two or more groups. So, for example, in an experiment on exposure to aggressive adults, children in one group might observe an adult model behaving aggressively, while children in a control group do not. And this brings back memories of Bandura and the Bobo dolls. And what they did was they compared two groups. One was those children who were exposed to aggressive acts in the model condition, and they looked at the mean number of aggressive acts. And then the other were those children who were not exposed to an adult who was engaged aggressively in the no model condition, and the mean is very different there. So let's talk about describing data. You can use frequency distributions, as you see here. Here are some good examples: pie charts, bar graphs, frequency polygons. Histograms, frequency distributions are also popular, where you can directly observe how your participants responded, and you can see what scores are most frequent, and you can look at the shape of the distribution, as you've seen with all of the things that I've just posted. But you can also look at outliers, which is really important. Let's talk about descriptive statistics. Descriptive statistics allow researchers to make precise statements about data. So they tell us, what is the most commonly occurring piece of data, what's the average, and these are very important. So two statistics are needed to describe data. One number describes the central tendency, or how participants scored overall, and then another describes variability, or how widely distributed the data is. Measures of central tendency, you don't, again, need to know this for the exam, but these are the mean, the median, and the mode, and I'll let you look at that on your own. And then variability is more important, and that is how much spread there is in a distribution. Standard deviation is simply just the average deviation of scores from the mean, another way of looking at variability. And this is small when most people have similar scores close to the mean, and it's large when people have scores further from the mean. Here's an example. When the standard deviation is small, most of the scores are very similar and close to the mean. But if it's large, most of the scores are away from the mean. Correlation coefficients are very popular in psychology, very important in our research. And it's important because we often are looking at the relationship between variables, and we want to know whether or not that relationship is weak or strong. And a correlation coefficient is simply just a number, a statistic that describes how strongly variables are related to one another, both in strength and in direction. And so we use the Pearson R correlation coefficient to most commonly describe that. Again, not going to ask you about that on an exam. It ranges from 0 to 1, positive or negative, and again, you get two pieces of information. The strength of the relationship between variables and the direction. If the direction is positive, both variables are going in the same direction. If it's negative, one variable is going in one direction, and the other variable is going in the opposite. And here's an illustration with intelligence scores, and the correlation coefficients range from the relationship between non-twin siblings who are raised apart, which is only 0.24, to 0.86 for the correlation between scores of identical twins. So obviously there is a strong relationship between intelligence and family patterns. So to calculate the correlation coefficient, you need to obtain pairs of observations from each subject. Each person has 2 scores, one on each variable, and you could use a fictitious example data set, such as the one I used earlier about seating pattern and grades. And this is just the ID number. This is their seating arrangement, whether they were in the first row, the second row, third, fourth, or fifth, and this is their exam score. And we ask, is there a relationship between seating and grades? That makes me a little dizzy, sorry. And, as I said earlier, there is, or tends to be. But here are the types of relationships that you could get. This would be a perfect positive relationship where everything is on a line, going in one direction, and this is a perfect negative relationship where as the values of one variable increase, the values of the other variable decrease. But who lives in a perfect world? None of us do. But a positive relationship looks more like this. You would draw a straight line through to see what the relationship looks like, but it would be scattered, but still generally in the same direction, moving positive. This is about a 0.65 relationship with the correlation coefficient, and this is about a negative 0.77, but again, a very strong relationship. No relationship would be, if you draw a straight line through here, there would be no way of looking at the relationship there. The correlation is 0. Some things to consider here: restriction of range, curvilinear relationships, and effect sizes. With restriction of range, the idea here is that you need to sample from the full range of possible values of both variables. So if you only looked at the upper level of scores, you're not going to get the full range of possible values, and as a result, the variable that you get with the correlation coefficient is going to be reduced. So, for example, if we used all of our data here, our correlation is negative 0.88. But if we only looked at the relationship using the first 2 rows, the correlation, because of range restriction, is 0, which is not a good thing. So restriction of range can be a serious problem. The other thing is curvilinear relationships, and the basic thing you want to know here is that a correlation coefficient isn't going to be able to detect curvilinear relationships. It's only going to give you information about linear relationships. So if you try to apply a correlation coefficient here, it would give you a 0. And then finally, the most important thing I'd like to impress upon you here is effect sizes. Researchers are most interested in being able to describe the strength of a relationship between variables. So the term that we use to describe that is effect size. And Pearson R is a measure, or correlation coefficients is a measure of effect size. So with effect sizes, if you have a correlation that is in the range of 0.2 to 0.2, that's what we would call 0.1 to 0.2. That's a small effect size. A medium effect size is a correlation of about 0.3. And then you have large effect sizes that are greater than 0.4. Another way of reporting correlation is to double it and to get variance, which is what you see here on the right. So transforming changes gives you a percentage which represents the variance and one variable that's accounted by the second variable. So, for example, if we were looking at the relationship between where you sit in a row and your grades, we could say that, and if this were our correlation coefficient, we could say that 50% of the grades were accounted for by your seating row. So that's it. That's all of our lectures, and I know I blew through this pretty quickly, but again, not too much that I wanted to focus on here because I don't expect you to know statistics and to test you on that. So again, thanks for your attention and take care. Bye-bye.